Hello, and welcome to Chapter 7, which deals with the central limit theorem. A positive. We're pretty much about past halfway, so congratulations, you've made it this far. Central limit theorem is about taking something and finding the averages of, like, continuing an experiment over and over and over again, and noticing that if I was to take multiple samples of the same size and then take the averages of those samples and use those averages as a single distribution, that distribution of samples of sample means, is also normal, will also be normal, which is very interesting. One of the cool examples of this is, let's say, for instance, you wanted to figure out how many blue M&Ms are there in a package of M&Ms, like the ones you buy at the like the grocery store or something, or like the, a single serving of M&Ms, like a bag, right? There actually is an average, but if you were to take multiple bags and find the number of M&Ms, let's say you take a classroom and you take 25 bags of M&Ms and you found the average amount of M&Ms per bag was like 20, and then you took another class and they all had bags of M&Ms and they took an average, and that would be like, let's say their average was 25, and so on and so on and so on. Those data points would be normally distributed. So it'd be really cool, because then you could kind of see, you could, compare and things like that. So the central limit theorem for sample means is basically that. So let's say here suppose you have a random variable with some distribution. We don't know it, or we might know it. Who knows? Could be anything. In this case, I'm going to just tie in the book here. The book uses this little x to mean the original, the mean of x. And we already know that sigma represents the standard deviation, and they have this little x right here to say that. They say that if you take random samples of size n from these values, as n increases, the random variable x bar, so this x bar consists of sample means. So let's say if you take one sample of size 30 and you take the mean of that sample, the average, that becomes like a new data point, okay? And if you take many of them, it appears to have a normal distribution with the same mean as the original, but now their standard deviation changes a little because you're taking average. So it's a standard deviation of the original divided by the square root of the sample size that you're taking. Okay, so let's look at this, for instance. So let's say if you keep drawing larger and larger samples and you calculate their means, the sample means form their own normal distribution. And it's also called the sampling distribution. Okay, and they have the same mean as the original, and the variance is equal to the original divided by the sample size, which makes sense because it's an average, right? Okay, so of course we would be dividing. So let's say here we take one die. Here are the chances of getting 1, 2, 3, 6, right? Let's say you had this many times. If you roll 2, your sample size of 2, you could get this many. 4, you get this many. And if you get 10, look how it approximates a normal distribution, okay? So in other words, if you draw random samples of size n, the distribution of samples, where now the data values isn't just like a data value, it's the means of each one, sample means, and the sampling distribution approaches a normal distribution. Okay, so what does that mean for us? What does that mean? Basically, we need to be able to calculate probabilities of the sample mean, and we're using central limit theorem to be able to do that. Okay, so so similar, we still use normal CDF to find probability. The only difference, and I want to make sure that you understand this, this is the key to 7.1 and actually 7.2 as well. The key is that, look, when you find the probability, you have the lower value still, okay? You still have that. You still enter the upper value. then the mean is the same as the original distribution. The only thing that changes is this here, this part, because the standard deviation is now considered the standard error of the mean, because we're talking about means now. So it's the original standard deviation divided by the square root of the sample size that you've taken, okay? So of course, where would we be without a super fun example? All right, so let's say here we want to do an unknown distribution that has a mean of 90. So this is the original mean, okay? And the original standard deviation, okay? And then samples of n equals 25 are drawn randomly. Find the probability that the sample mean is between 85 and 92. So before, if we were just finding the regular probability of some sample or find the probability that x is between 85 and 92, but in this case, the variable. Okay, so for this example, we're finding the probability that a sample mean is between 85 and 92, emphasis on the word sample mean. So this is different than what we did in chapter 6, but similar, okay? Similar in the sense that, yes, we're still using normal CDF, but because we're talking about sample means here, what we enter for the standard distribution is a little different. The deviation, I mean, is a little different. I'm sorry. So we still do, as before, second distribution. We go to normal CDF. Okay, fine. Then we do lower and upper limit still. So this is between 85 and 92. Now, according to central limit theorem for sample means, the mean is still the same. So in this case, the mean is 90. Now, what changes, it's the standard error of the mean, okay? So remember that is the original standard deviation for the original distribution, that's 15, and that's going to be over, so we divide that by the square root of your sample size. And in this case, the samples are size 25. So there we go. So you just have to enter it that way. I mean, you could have solved. Okay, so for this example, we're finding the probability that a sample mean is between 85 and 92. Emphasis on the word sample mean. So this is different than what we did in chapter 6, but similar, okay? Similar in the sense that, yes, we're still using normal CDF, but because we're talking about sample means here, what we enter for the standard distribution is a little different. The deviation, I mean, is a little different. I'm sorry. So we still do, as before, second distribution. We go to normal CDF. Okay, fine. Then we do lower and upper limit still. So this is between 85 and 92. Now, according to central limit theorem for sample means, the mean is still the same. So in this case, the mean is 90. Now, what changes, it's the standard error of the mean, okay? So remember that is the original standard deviation for the original distribution, that's 15, and that's going to be over, so we divide that by the square root of your sample size. And in this case, the samples are size 25. So there we go. So you just have to enter it that way. I mean, you could have solved it. For those that appreciate math humor, if you really look at this closely, this is actually just 3, but it's fine. Okay, so then you have pasted just like before, and you hit enter. And there it is. Okay, so for this example, we're finding the probability. Sorry. So, okay. So let's see here. Another example that you might find in Newton or in your textbook, let's say we have an unknown distribution with a mean of 90 and a standard deviation of 15, and that samples of size n equals 25 are drawn randomly. It says find the value that is 2 standard deviations above the expected value 90 of the sample mean. So we're going to be using, usually we do the mean plus the number of standard deviations times however many whatever standard deviation is. But in this case, because we're talking about sample means, our new standard deviation, you can think of it that way, is the original standard deviation divided by square root of n. Think of it like the standard deviation, or some people call it standard error of the mean, could have this little bar right here, is equal to the original, okay, over the square root of whatever it is, the sample size, okay, and that's all given in the problem. Okay, yeah, so basically we want to know what is 2 standard deviations above 90. So it's just 90 plus 2 times this this standard deviation, because we're talking about sample mean. Okay, so notice sample mean, what is the, x bar represents mean, so sample mean, and there it is. Okay, so it would be 96 in this case. All right. Here, the length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of half an hour, right? 0.5 hours. A sample of size n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 and 2.3 hours. Okay, so here we go. So let's first, when you have these types of problems, it's really good to be able to just read it and extract all the information from it. Okay, we know we're doing central limit theorem problems. Okay, so we know we have, okay, here, we're given an original distribution, it's normal. The mean is 2, okay, fine, that's 2. The standard deviation is 0.5, okay, that's fine, we got that. Then the sample size is 50, so n is 50, okay? Then we say x bar, this actually should have a bar over it, is normally distributed with a mean of 2, so same as the original, and a new standard deviation of square root of sigma over square root of n. So the original standard deviation divided by the square root of sample of 50, okay? So why do we know to do this? Because it's asking the probability of the sample mean. So that's the keywords that tell us, oh, we need to use a different deviation, okay? So we're finding the probability that the sample mean is between Okay, so for this example, we are doing the probability that the sample mean is between 1.8 and 2.3. So let me show you how to do that. Again, we hit second, distribution, go to normal CDF, hit enter. Okay, now in this case, our lower bound is going to be 1.8. Our upper bound is 2.3. So boom, we enter that. Then go down to our mean. Remember, according to central limit theorem, the mean is the same, okay, as the original distribution. So in this case, it's 2, all right? And then remember the standard error of the mean. It's the standard distribution, the standard deviation of the original normal distribution over the square root of the sample size of our samples. So in this case, our standard deviation of the original was 0.5. Okay, so for this example, okay, great. So here, to find percentiles, we do the same thing as before. We're going to use inverse norm. The only difference is, you guessed it, is that the new standard deviation is going to be the original over square root of the sample size. Okay, so this is when you want to find percentiles for means, right? Okay, so K is the percentile, mean is the original mean, sigma is the original standard deviation, and then N is the sample size. Okay, so let's go ahead and do an example. We're going to get to this in a second. All right, so let's see here. In a recent study reported October 29th on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15. Let's take a sample size of N is equal to 100. What are the mean and standard deviation for the sample mean ages of tablet users? So right away, when you see the keyword sample mean, you should think to yourselves, okay, I'm going to use central limit theorem. And so central limit theorem for means is that the mean of the sampling distribution, right? So I could do this little X bar to say that, hey, it's going to be equal to the original mean. Okay, so the original mean. And the standard deviation for the sampling distribution, okay, this is X bar, sorry, is going to be equal to the original distribution over square root of the sample size that you're taking. Okay, so that's that. All right, so here it is. So yeah, so here it is. They wrote it. Okay, fine. 34, and the sample standard deviation is given by, and then this is this should have a little bar in front of it. Again, this is a typo on the book's part. This should have a bar. Sigma over square root of n, 15 over square root of 100, which is 1.5. Okay, great. All right, so what does the distribution look like? Well, if you're talking about sampling, right, the central limit theorem, what does that tell us? It tells us that if n is large enough, the sampling distribution will be approximately normal. Okay, so you would say, oh, this is approximately normal. Okay, so then here it says, find the probability that the sample mean age is more than 30 years. Okay, so in other words, we want to find X bar greater than 30. This should be a bar. Hello. Okay, so we're going to go ahead and do this normal CDF. Remember, e to the 99 is another way of saying 10 to the 99. Same situation. Now, what if we want to find the 95th percentile? So if you want to find the 95th percentile, that's an inverse norm problem. So let's go ahead and do that. Okay, so we're trying to find that, so you do, and that's it for 7.1. The homework is 1 through 6 all. Enjoy, and I will see you on the next video. Second, distribution, go to inverse norm, select that. The area, it's 95%, so the area is going to be 0.95. Okay, The mean in this situation is 34, right? CLT, central limit theorem, same mean. The new standard deviation is the old one over square root of 100. And parentheses, okay, it's going to be on the left. We're talking about percentile. Then you hit enter on paste, hit enter again, and there it is. Your 95th percentile is 36.5 years. Okay? So what we do here, we do second, right, distribution, normal CDF, hit enter. Lower bound is now going to be 30, okay? Upper bound is going to be 10 to the 99 because we're going all the way to the right, okay? And then our mean is 34, okay? And our standard deviation is now going to be 15 over square root of 100, okay? What we calculated in part B. But let's just go ahead and enter it the regular way, square root of 100. Okay, and then you hit close parentheses and you hit enter. You hit paste. Go to paste and hit enter. Then hit enter again, and then you get the value, which is 0.9962.
We are doing the probability that the sample mean is between 1.8 and 2.3. So let me show you how to do that. Again, we hit second, distribution, go to normal CDF, hit enter. Okay. Now in this case, our lower bound is going to be 1.8. Our upper bound is 2.3. So boom, we enter that. Then go down to our mean. Remember, according to central limit theorem, the mean is the same, okay, as the original distribution. So in this case, it's 2. All right. And then remember the standard error of the mean. It's the standard distribution, the standard deviation of the original normal distribution over the square root of the sample size of our samples. So in this case, our standard deviation of the original was 0.5. Okay, and then we're going to write that over second. Here's the square root key, and the size of the samples was 50, so we're going to enter that. Okay, close it, and then you just hit scroll onto paste and hit that, and there it is, normal CDF. Here's our lower bound, here's our upper bound, here's our mean, and then here's our standard error of the mean, okay, according to central limit theorem, and then you just hit enter, and there it is, this is the probability that the mean time is between 1.8 and 2.3 hours, so it's 99.8%.
Yeah, so then basically we have here normal CDF, lower value, upper value, mean, standard error of the mean, and in this case the standard error of the mean is 15 over square root of 25. And there it is, 0.6997, so 69.97%.